I want you to do something for a second. Just look at the device you're using right now.
Yeah, the actual physical piece of technology you're listening to this on.
Right. I mean, it feels weighty in your hand, right? It feels dense. It feels real.
It definitely feels like a solid, continuous object.
But what if I told you that you were holding overwhelmingly empty space? Like
Yeah.
the solid device in your hand, the chair you're sitting on, the floor beneath your feet, even your own body, it's almost entirely nothingness.
Which is a reality that, completely defies human intuition. I mean, our brains are biologically hardwired to trust our senses,
Right.
and our hands tell us that a table is a solid block of matter. But when you strip away that illusion, physics reveals a very, very different landscape underneath.
And that hidden landscape is exactly what we are exploring today. Welcome to the deep dive.
Glad to be here.
I know you've been furiously prepping for your TEAS or HESI nursing entrance exams, and, well, we know how notoriously tricky those science sections can be.
Oh, they are brutal.
Yeah, you're trying to memorize these completely invisible concepts. So today, we're giving you the ultimate cheat code. We're going straight inside the atom.
Which is really the foundation of everything else you'll study.
Exactly. We're going to figure out how it's actually built, protons, neutrons, electrons, and we're going to explore the incredibly messy, error-filled, and just utterly fascinating history of how humanity figured all of this out.
It is quite a dramatic journey, honestly. But before we get into the historical detective story, we really should lay out the basic foundational framework.
Yeah, let's start with the basics.
So when we talk about an atom today, we are talking about a central nucleus. And that nucleus contains positively charged protons and electrically neutral neutrons.
Right, tightly packed in the center.
Exactly. And surrounding that dense nucleus, you have this vast cloud of negatively charged electrons.
Which, I mean, sounds so tidy when you say it like that.
Yeah.
But the definition of an atom has been a moving target for millennia.
Oh, absolutely.
We're talking about 2,400 years of evolution here. I mean, we started with the ancient Greeks, Leucippus and Democritus, in the 5th century BCE, and they called it atomos.
Which literally translates to uncuttable.
Uncuttable, right. To them, it was the absolute smallest indivisible unit of matter. Like, you just couldn't break it down any further.
And that philosophical assumption basically held up completely unchallenged until about 1897.
Which is wild to think about. And now we've gone from an uncuttable solid ball to a quantum probability cloud governed by, invisible nuclear forces.
Yeah, and for exam purposes, a lot of tests will still let you get away with visualizing the simplified planetary-style model.
Like the Jimmy Neutron logo?
Exactly. A nucleus in the middle with electrons orbiting it like tiny planets around a sun. But scientists consider that a massive approximation. It's not the literal truth of what is happening down at the subatomic level.
Okay, let's unpack this. Because if we want to understand how atoms interact, especially how they interact in the human body, which is just critical for your clinical preps, we have to know how to count their parts.
Yes, the accounting system.
Right, and this specific accounting system is arguably the single most common trap on standardized science exams. We really need to talk about atomic number versus mass number.
That is the ultimate pitfall for test takers. I mean, it trips people up constantly, but it makes perfect sense once you look at the actual mechanics of the atomic ledger.
So walk us through it.
First, you have the atomic number, which is usually represented on the periodic table by the letter Z. This is strictly the number of protons in the nucleus.
Just the protons.
Just the protons. The atomic number is the ultimate identity card of an atom. It defines exactly which element you're looking at with no exceptions. If it has 1 proton, it's hydrogen.
And if it has 6 protons, it's carbon.
Exactly.
So if I change the number of protons, I am literally transmuting it into a completely different element.
You are.
Okay, so if the atomic number is just the protons, I'm guessing the mass number is just like everything else dumped together, protons, neutrons, electrons, the whole physical weight of the atom.
See, that is a very logical assumption, but it's exactly where the exam traps you.
Oh, really?
Yeah. The mass number, represented by the letter A, is strictly the total number of protons plus the number of neutrons. It only accounts for the heavy material inside the nucleus.
Wait, why wouldn't you count the electrons? If they are physically part of the atom, shouldn't they, add to the overall mass?
Well, in a normal uncharged atom, the number of electrons does equal the number of protons. That's why their positive and negative charges completely cancel each other out, making the atom neutral.
Right.
But here is the physical reality. An electron has a mass of about 1 over 1,836 of a proton's mass.
Wait, 1 over 1,800? That's incredible. So if a proton is a bowling ball, an electron is barely a grain of sand.
Exactly the right scale. So for any standard weight calculations, the mass of the electrons is functionally zero. You completely ignore them when weighing an atom.
Wow, okay.
But, as we will explore shortly, they are the sole drivers of chemical
Okay,
reactions.
wait. Hearing you explain that, it sounds exactly like a city's zip code versus its total population.
Oh, I like that.
Yeah, like the zip code, the protons tells you exactly where and what the city is. It's the core identity. But the population, the mass number, includes everyone living inside the city limits, both the protons and the neutrons.
That works perfectly, actually. The zip code never changes for that specific city, but the population of neutrons can fluctuate a bit
Mhm.
without changing the city's identity on the map.
And to anchor this in the real world, the sources bring up carbon-12. It has 6 protons, 6 neutrons, and 6 electrons.
Right.
So its atomic number is 6, which makes it carbon. Its mass number is 12, because 6 protons plus 6 neutrons equals 12. And we just completely ignore the 6 electrons for the weight.
Spot on.
And carbon-12 is actually the universal anchor for
Yeah.
all of chemistry, right?
Yeah.
I mean, one atomic mass unit, or MU, is officially defined as exactly 1/12 the mass of a single carbon-12 atom.
It is. It's the standard reference weight for the entire periodic table.
But hold on, I have to challenge something here because the physics of the nucleus seem completely broken to me.
How so?
Well, if the mass is just this insanely dense cluster of protons and neutrons packed into the center, and all protons are positively charged, shouldn't they violently repel each other?
Ah, yes.
Like if you push two positive ends of a magnet together, they fight back hard. How does this incredibly dense nucleus not just detonate itself instantly?
Physicists were actually stuck on that exact paradox for years. By all the classical laws of electromagnetism, a nucleus packed with positive charges should act like a bomb and blast apart.
Right.
The fact that it doesn't reveals the existence of something called the strong nuclear force.
The strong nuclear force.
Yes. It is a fundamental force of nature that only operates at incredibly microscopic distances, specifically just across the tiny diameter of a nucleus.
Okay.
And at that specific ultra-short range, it is so overwhelmingly powerful that it completely overrules the electrical repulsion, pushing those positively charged protons apart.
So it just overpowers the magnets.
Exactly. It acts like an immensely powerful high-tension spring just binding protons and neutrons together.
That is wild. There is a microscopic tug of war happening inside every single atom in our bodies. And this localized cosmic glue is just barely winning.
That's a great way to picture it.
But it's crazy to think we take this incredibly complex framework for granted now. I mean, getting to this understanding wasn't just a sudden realization. The history of atomic structure is really just a graveyard of scientific models being demolished one by one.
It was a very messy trial and error process. I mean, the first major modern breakthrough came from John Dalton, an English chemist, around 1803.
The billiard ball guy?
Right. He proposed the billiard ball model. He treated the atom as a solid, featureless sphere. And, we have to give him credit because this was a huge leap forward at the time.
Because it explained chemical reactions.
Yes, it beautifully explained the law of definite proportions, the idea that chemical reactions are just atoms rearranging in fixed whole number ratios.
So if you mix hydrogen and oxygen to make water, it always takes the exact same ratio of billiard balls.
Exactly.
But he still thought they were completely solid, uncuttable spheres.
Right. And that held until 1897 when J.J. Thomson, who was working at the Cavendish Laboratory in Cambridge, completely broke the billiard ball concept.
How did he do that?
He was playing around with something called a cathode ray tube. Basically, he took a sealed glass tube, pumped most of the air out to create a vacuum, and ran a high-voltage electric current through it.
And a mysterious glowing beam shot across the inside of the tube.
A cathode ray. But what Thomson did next was revolutionary. He put magnets around the outside of the glass tube and realized he could actually bend the glowing beam.
Oh, wow.
Yeah, and because the beam bent toward the positive end of a magnet, he deduced that the beam wasn't just light, it was a stream of incredibly tiny, negatively charged particles.
He discovered the electron.
He did. He realized he could literally rip these tiny negative particles out of the atoms of every single element he tested.
Which shatters Dalton's model instantly. Because if you can pull a piece out of an atom, it isn't an indivisible billiard ball. It has internal structure.
Exactly. So Thomson pivots, and he proposes what became known as the plum pudding model.
I always love that name.
It's very descriptive. He suggests the atom is just this diffuse, puffy cloud of positive charge with these tiny negative electrons studded randomly throughout it, like pieces of fruit suspended in a bowl of pudding.
It makes sense based on what he knew, but that model met a very sudden end between 1909 and 1911.
It really did.
Ernest Rutherford, along with his students, Hans Geiger and Ernest Marsden, were working at the University of Manchester. And they set up the now legendary gold foil experiment.
Yes, a massive turning point in physics.
And the context of this experiment is arguably my favorite detail from all the sources. Rutherford didn't set out to rewrite physics. He assigned this to his students as a training exercise.
Right, it was supposed to be busy work.
Yeah. He told them to take a lead box containing a radioactive rock that shot out positively charged alpha particles, basically microscopic, heavy bullets, and fire them at an incredibly thin sheet of gold foil, only a few hundred atoms thick.
And based on Thomson's plum pudding model, Rutherford fully expected the heavy alpha bullets to rip straight through the diffuse positive clouds of the gold atoms, maybe with a slight deflection here or there.
But they hit a brick wall.
Well, not all of them. Most passed straight through. But Geiger reported something impossible. Roughly 1 in every 8,000 alpha particles hit the gold foil and bounced almost straight back toward the source.
I just can't even imagine the confusion in that lab. I mean, Rutherford's reaction is legendary. He later described the shock of it by saying, quote, "It was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you."
It took Rutherford about 2 years to actually work out the mathematics of what his students had witnessed.
2 years of just crunching the numbers.
Yeah, and he proved that this violent bounce-back effect could only happen if almost all of the atom's mass and absolutely all of its positive charge was concentrated in a shockingly tiny, incredibly dense central nucleus.
So the alpha bullets were bouncing back because they were getting a direct hit on this microscopic core.
Precisely.
So if we scale this up so you can really visualize what Rutherford discovered, if an atom is the size of a massive professional football stadium, the nucleus is a single marble sitting right on the 50-yard line.
And the electrons.
There are microscopic dust specks swirling around way up in the highest outer nosebleed seats. Everything else, the massive field, the lower bowls, the entire concourse is just dead, empty space.
Which completely redefines our relationship with physical reality. It proved that solid matter only feels solid because of the electromagnetic repulsion between electron clouds.
That is just so counterintuitive.
It really is. When you rest your arm on a table, the atoms in your skin are not actually physically impacting the atoms of the wood. The negative electron clouds in your arm are simply repelling the negative electron clouds at the table.
So you're experiencing a force interaction, not solid objects packed with material.
Exactly.
That completely scrambles the brain. Every time I touch a surface, I'm just feeling invisible magnetic pushback. But Rutherford's new planetary model, the tiny marble nucleus with electrons orbiting it like planets, it had a massive fatal flaw.
It did. And this is where classical physics had a real existential crisis.
Because if electrons are constantly orbiting in a circle, classical physics says they should continuously radiate and lose energy. And if they're losing energy, they should spiral inward and crash right into the nucleus in a fraction of a millisecond.
The classical atomic collapse problem.
Right. If Rutherford was totally right, all matter in the universe should instantly self-destruct.
That tension was the core of the physics crisis in the early 20th century. And the solution arrived in 1913 from Niels Bohr, a brilliant Danish physicist who had actually come to work with Rutherford.
What was his fix?
Bohr proposed a radical idea. Electrons can only occupy specific, fixed energy levels.
Like an elevator in a building.
That is a great way to picture it. Instead of a smooth ramp where you can exist at any height, the electron is in an elevator. It can be on floor 1 or floor 2, but it is physically impossible for it to hover in the empty elevator shaft between the floors.
Oh, that makes sense.
And crucially, Bohr realized electrons don't bleed energy while they are resting on their specific floors. They only absorb or release energy in the form of a photon of light when they instantly jump or teleport between the floors.
The famous quantum leap. You disappear from floor 1 and instantly reappear on floor 2 without crossing the space in between.
That solves the collapse crisis, yes.
But the physics get even weirder. By the 1920s, scientists like Erwin Schrödinger and Werner Heisenberg step in and prove that even Bohr's neat, fixed circular elevator tracks were wrong.
Yeah, the full quantum mechanical model completely replaced Bohr's idea. Heisenberg introduced the uncertainty principle in 1927, which proved mathematically that you can never know both the exact position and the exact momentum of an electron at the same time.
Because the act of measuring one blurs the other.
Right. So electrons do not travel in predictable planetary orbits. They exist in three-dimensional probability clouds called orbitals.
Probability clouds.
Yes. We can calculate the likelihood of finding an electron in a specific region of space, but we can never map a distinct path.
It's just a blurry zone where the electron probably is. And then James Chadwick finally discovered the neutral neutron in 1932, which completed our modern map of the nucleus.
It was the final piece of that puzzle.
But here's where it gets really interesting to me. If the planetary model of the atom, the neat one with the little solid electron dots circling the nucleus, like a mini solar system, if that was abandoned by scientists in the 1920s, why is it still absolutely everywhere?
It is everywhere.
It's the symbol for nuclear power. It's in every sci-fi movie. It's literally the official logo for the International Atomic Energy Agency.
Well, it survives entirely because of visual intuition. It's clean, it's easy to draw on a chalkboard, and it instantly communicates the abstract concept of atomic energy.
Yeah, makes sense.
But scientifically, it is completely outdated. And this is a crucial takeaway for your nursing exam. When a test asks about electron shells, you must always view them as probability zones or electron clouds, never as fixed, solid racetracks.
Write that down, seriously. Okay, so now that we have the accurate quantum map of the atom, the dense nucleus in the center, the sprawling probability cloud on the outside, let's look at what happens when you start tweaking the recipe.
The chemistry.
Right, when you add or subtract particles.
Yeah.
Because this is where the actual biology and chemistry of the human body happens.
And there is one absolute unbreakable rule before we start tweaking. Rule number 1 is that you never change the proton in ordinary chemistry.
Right, because as we discussed, changing the protons changes the identity of the element. That is nuclear transmutation.
Exactly.
That doesn't happen when you digest a sandwich or mix chemicals in a beaker, but you can change the neutrons and the electrons. Let's talk about changing neutrons first.
Okay, neutrons.
When you have atoms of the exact same element, meaning they have the exact same number of protons, but they have different numbers of neutrons, those are called isotopes.
Yes, isotopes.
Their mass gets heavier or lighter, but their identity on the periodic table stays exactly the same.
Let's use hydrogen's isotopes as the clearest example here. Ordinary hydrogen, which is called protium, is incredibly simple. 1 proton, 0 neutrons.
Just a single proton.
Right. But if you force 1 neutron into that nucleus, you get an isotope called deuterium. Deuterium is used to make heavy water. It is chemically still water, but the hydrogen atoms are literally heavier, and it's used as a moderator to slow down reactions in nuclear power plants.
And if you force 2 neutrons in there with that single proton, you get tritium. Tritium is highly unstable and radioactive.
Very radioactive.
It has a half-life of about 12.3 years. And because it constantly emits a glow as it decays, we use it in self-illuminating exit signs.
The clinical and scientific applications of isotopes are profound, actually, particularly with carbon-14.
Oh, radiocarbon dating.
Exactly. Normal carbon is carbon-12, 6 protons, 6 neutrons. But carbon-14 has 6 protons and 8 neutrons. That imbalance makes it radioactive, meaning it decays over time, but it decays at an incredibly steady, predictable rate with a half-life of about 5,730 years.
Which is the entire basis for radiocarbon dating. Like living things, plants, animals, as we are constantly absorbing carbon-14 from the atmosphere while we are alive.
Breathing it in, eating it.
Right, but the exact moment an organism dies, it stops taking in new carbon. And the carbon-14 that is already trapped inside it just slowly ticks away, decaying like an internal biological stopwatch.
It's fascinating.
Archaeologists just measure how much is left to calculate when the thing died. The sources mention they used this exact method in the 1990s to date the linen wrappings of the Dead Sea Scrolls, confirming they were actually 2,000 years old.
It is a brilliant application of nuclear chemistry. But we need to bust a major misconception right now because exams love to test this.
Okay, what is it?
Many students assume that because isotopes have different masses and because some are radioactive, they must act completely differently when they mix with other chemicals.
But they don't.
Exactly. Isotopes behave almost identically in chemical reactions. Deuterium still bonds perfectly with oxygen to make water. Carbon-14 forms the exact same biological structures as carbon-12.
And the reason why is so elegant, chemistry is driven purely by the electrons, not the neutrons. The neutrons are locked deep inside the nucleus, just adding dead weight. The electrons in the outer clouds are the ones actually socializing and bumping into other atoms. Which brings us perfectly to the other way we can tweak the recipe-changing electrons.
Right, creating ions.
Exactly. When an atom gains or loses an electron, it creates a chemical electrical charge. We call these charged atoms ions.
And since electrons carry a negative charge, the math is a bit counterintuitive here. Losing electrons means you are subtracting negative energy, which leaves the atom with an overall net positive charge.
Right, losing a negative makes you positive.
Yes. We call a positively charged ion a cation. Conversely, gaining extra electrons gives the atom a net negative charge, and we call that an anion.
But why are they doing this? Why is an atom just throwing away pieces of itself or stealing from its neighbors?
It comes down to something called the octet rule.
The octet rule.
Yes. Atoms desperately want full outermost valence shells, which for most elements means having exactly 8 electrons. They just want structural stability.
And the classic example of this is sodium chloride ordinary table salt. Sodium has an atomic number of 11. If you map out its electron clouds, it has one lonely electron in its outermost shell.
Just hanging out there.
Right, and it desperately wants to get rid of it so it can drop down to its perfectly full, stable lower shell. Chlorine, on the other hand, has an atomic number of 17. It has exactly 7 electrons in its outer shell. It is ravenously hunting for one single electron to reach that perfect 8.
It's the ultimate match made in heaven.
It really is. Sodium gladly throws its electron away and becomes a positive anation. Chlorine snatches that electron up and becomes a negative anion. And because opposite charges naturally attract each other, that electrostatic magnetic pole locks them fiercely together in an ionic bond. Boom, you have table salt.
And that exact electrostatic interaction is not just about seasoning your food. It is the fundamental driving force of human biology.
Which brings us to the most important question for you, the listener, especially if you are stepping into a clinical setting or walking into that nursing exam. I mean, this electron and proton accounting can sound like abstract, invisible textbook theory, but it is literally the operating code of medicine.
If you look at any standard metabolic or electrolyte panel in a hospital, when you see lab results measuring sodium, potassium, calcium, or chloride, you are looking at a direct report on ion concentrations in your patient's blood.
They're just charged atoms.
Yes, and those ions regulate absolutely everything. The positive charge of a sodium ion flowing across a cellular membrane creates the action potential that drives nerve conduction, allowing your brain to send signals.
Wow.
Calcium ions control the muscle contractions that allow your heart to beat. Chloride ions maintain fluid balance and cellular homeostasis. Biological life as we know it is entirely dependent on atoms constantly trading electrons.
Think about something as routine as hanging an IV drip of normal saline. The reason it successfully hydrates a patient without destroying their cells is because those sodium and chloride ions dissolve in the water and perfectly match the electrically charged cellular environment inside the body.
Precisely.
If you don't understand atomic structure, you literally don't understand how IV fluids work on a cellular level.
And beyond basic biochemistry, we also rely on the instability of the nucleus. Radioactive isotopes make modern diagnostic medicine possible.
Like what?
Well, unstable proton-neutron ratios and iodine-131 allow us to target and treat thyroid conditions. Technetium-99 meters is the backbone of millions of diagnostic imaging scans every year. Cobalt-60 emits radiation that is crucial for targeted cancer therapy.
That it goes even further into everyday medical tech, MRI machines. The M stands for magnetic. They rely entirely on the natural magnetic behavior of hydrogen nuclei, which remember are just single protons swarming around inside the water molecules in our bodies.
It's incredible when you think about it.
Even the smoke detector keeping you safe in your house right now is actively using atomic structure. It relies on a microscopic amount of the radioactive isotope americium-241 to detect smoke particles disrupting an ion current.
It scales from the microscopic to the macroscopic seamlessly. From the smallest neuron firing in your brain to the most advanced diagnostic machine in a hospital wing, everything operates on the strict accounting rules dictated by protons, neutrons, and electrons.
Okay, we have covered an incredible amount of ground today. Let's do a rapid-fire recap specifically for your exam prep. Core takeaways to lock in. Protons define the absolute identity of the element. Neutrons determine the isotope and the mass. Electrons determine the charge and drive all the chemical behavior.
And do not fall for the accounting trap. Atomic number Z is just the protons. Mass number A is protons plus the neutrons.
Toss out that planetary model electron shells are three-dimensional probability clouds. Ions only ever form by changing the number of electrons, never the protons. And above all, everything you see and touch is almost entirely empty space.
It forces you to completely reevaluate the physical world.
It really does. And I want to leave you with one final thought to mull over. Building on that idea of empty space, we established that the atoms making up your body, the device in your hand, and the stars in the sky are 99.99% empty space.
Yes.
Next time you knock on a wooden door or sit in a chair, think about Rutherford's marble in the stadium. You aren't actually touching solid stuff. The atoms in your hand and the atoms in that chair are overwhelmingly empty space.
Just clouds repelling clouds.
Exactly. What you are physically feeling is just the invisible electromagnetic force of electron clouds pushing back against each other. You are essentially hovering on a cushion of quantum probability.
That is a staggering perspective to walk away with.
Something to think about the next time you look in a mirror or study a periodic table. Thank you for joining us on this deep dive. Keep crushing your exam prep, keep questioning the world around you, and we will catch you on the next one.